Welcome back, AP Calc AP students. Mr. Record here. We're going to take a look at our fifth example from our combo topic lesson 6.4 and 6.5, but really we're more into 6.5 at this point, which is about investigating behaviors of area and the accumulation function. But really what I have called these are my rate in and rate out problems. I like to really get on top of these and start to teach these to students when we're in Unit 6, even though they do come up again in Unit 8. They're so important. You're going to see them on the AP exam. It's typically going to be a question 1 or a question 2 in any given normal year. And like any calculus teacher across the country, we want you guys to be very comfortable with these. So what do you say? Let's go to the zoo. So our problem number 5 here, lions and tigers and bears, oh my. The rate at which people enter the Indianapolis Zoo on a given day is modeled by the function e, and e is defined by e of t is equal to 23 times the natural log of t squared plus 3t plus 1. The rate at which people leave the zoo on the same day is modeled by the function L, modeled by the equation L of t is equal to 63 plus 50 times the inverse tangent of t minus 6 over 2. Both E of t and L of t are measured in people per hour, and time t is measured in hours after 8 a.m. These functions are valid from time 0 to time 12, which is the hours during which the zoo is open. At time t equals 0, there are no people in the zoo. So our first question is going to ask how many people have entered the zoo by 12 o'clock p.m., which, to help you out, we've declared that to be time t equal 4. Question B, 20% of those people who leave the zoo are selected at random to receive a special discount ticket for a return trip. How many people have received a discount ticket by 5 p.m. or t equal 9? Part C is going to define a new function n of t as the definite integral from 0 to t for e to the x minus L of x. E of x minus L of x for time 0 to 12. Find the value of n of 10 and explain the meaning of n of 10 in the context. And find n prime of 10 and explain its meaning in the context. And finally, at what time t between 0 and 12 does the model predict the number of people in the zoo is at a maximum? Justify your answer. So you see 4 really common parts to this free response question. And what's really beautiful about this is that we are finally deep enough into our course that you can tackle this full-blown free response question because you know how to do each part. So let's take a look at part A. Now, because we see a very complicated E of t and L of t, that's why that this is a calculator active question. There's no doubt about that. And we're going to want to use our calculator to define these particular functions. So the first thing that we're going to do, jump to the calculator and do just that. Doesn't matter which one we throw in here first. Let's go with the E of t. So we have E of t. Now the calculator that I'm using, the Inspire, is not case sensitive, so don't worry about trying to get a capital letter because it'll go away as soon as you hit enter anyway. So E of t is 23 times the natural log of the quantity t squared plus 3t plus 1. If you are using a TI-84, then you're going to enter this into your Y1 menu. You just might want to be careful and use the variable x instead of t. Let's do the same thing for our L of t. L of t, control math template, will give our colon equal. And then we have 63 plus 50 times inverse tangent of the fraction. Let's get that fraction in here. T minus 6 all divided by 2. Now, I can't emphasize this aspect enough. You want to make sure that these two functions are entered correctly. So you want to double check E of t on your paper, look at your calculator screen, double check L of t on your paper, look at your calculator screen. That extra 5 seconds that it would take to verify that could really save you a lot of heartache in case you had entered these wrong. Because as a reader, we really are going to have a hard time giving some partial credit for a bunch of functions that you had potentially entered incorrectly. So we have this guy. We're going to return back to our problem. I'm going to read that part A. How many people have entered the zoo by 12? Well, what is it that we need to know about this? Well, the number of people that have entered is certainly going to be tied to this enter equation. And we have to keep in mind that this enter equation is a rate. It is the rate at which people enter. It doesn't look like a rate in that it doesn't have a derivative attached to it, but we want to interpret it as such. And so if we have a rate and we want to get a total amount, we have learned that we just need to integrate that rate. We integrate starting at the very opening moment of the zoo at time 0, that would be 8 a.m., and we would end at 12 p.m., that's noon, or time 4. Now, you would have to write this on your paper in order to receive your first point. In fact, what I've written right there earns the first point on a normal AP Calc exam. You don't have to write the entire detailed expression for E of t since it's already defined, and it's probably quicker that you don't. Now we know that this is going to probably be an approximation. If you wrote an equals there, that's okay. But I'm betting that this is probably a decimal answer, judging at how ugly that expression is up there. So let's return to our calculator, and we'll use either our Math 9 setting from the TI 84 or Shift plus. Throw in 0 to 4 as your boundaries, and then you just throw in that E of t with respect to t, and it's going to give you an exact answer that you can hit Control Enter to convert to your approximated answer. And so we're getting 203.068 as our result. Now I know that it probably seems kind of crazy that you can have 0.068 of a person, but honestly, if the problem doesn't say to round to the nearest person, don't do it. Don't go for it. Don't just leave it as a decimal and just call it that. It would be nice to give it a label, and in this case, that label would be people, because we've essentially taken E, which is people per hour, and we've multiplied by this change in time, which is hours, and that would be people. The integral just adds many of those increments up as if we were kind of looking at this in small increments of time, almost like finding the area of a large shape in small increments of rectangles. It's the same idea. That takes care of part A. 2 points very likely would be earned. Let's take a look at part B. 20% of those people who leave the zoo are selected at random to receive a special discount ticket. How many people have received that by 5? Well, in this particular case, you want to make sure that you draw your attention to the leaving function, the L function. So what that means is we're going to integrate L of t with respect to t. Now, the boundaries over which we're going to do that are going to start at time 0, and 9 hours later, after 8 a.m., would indeed be 5 p.m. Now, the 20% sometimes bothers students, and I really hope that it wouldn't, because all you're simply doing is just taking 20% as a scalar multiple. Right? Whatever this total amount would be of the people that left, 20% of those would be what we would calculate by multiplying by 0.2. So we are just going to move to the calculator. We can enter in our 0.2, multiply by the definite integral, Shift plus, from 0 to 9, and isn't it lovely that we have our L already defined? L of t. That looks like a 1, doesn't it? But that's actually an L that I've entered. It's bold because the calculator recognizes it. We'll integrate with respect to t, and if we want an exact answer, Control Enter will take care of that at 79.180, and that would be our answer. That's how many discount tickets that we're dishing out. Come back to the zoo. Okay, now things are going to start to get a little bit more interesting as we move to some of the future parts. Now we got part C, which looks a little complicated. We're defining a new function n of t, and we say that it's the integral of e of x minus L of x from 0 to t. What does n of 10 equal, and what does it mean? Well, to find the n of 10, I don't think that that's necessarily going to be too bothersome, because it seems like we just replace the 10 in the integral symbol with the t, I'm sorry, in the integral with 10, and we still have our e function minus our L function. And if anybody's wondering about, oh gosh, the variable has changed, that's no good, I wouldn't worry about that. We need to use a dummy variable of x here if we impose a time variable in our boundaries. That's something that you don't have to really worry yourself on the AP exam. If a student wrote t's in these two spots, you wouldn't be penalized. All you need to do is make sure that you calculate this with your calculator correctly. So let's go ahead and do that. And so we've got a definite integral, so shift plus, and we're going from 0 to 10. And I would go ahead and put a parenthesis in here because we're taking the quantity e. And now here's where I'm going to have to alter my plan a little bit. I have defined my functions, if you remember earlier. I can scroll up and show you they're in terms of t. And so I want to keep consistent with that. I don't want the calculator to be confused. So I have to use my t's. And I want e of t first, and I want L of t next. With respect to t, and this exact value can be approximated now to 273.635. But what does that mean? That's a good question. What does it mean? Well, think about it. You've taken the rate at which people were entering minus the rate at which people were leaving and integrate it. So you essentially have the total amount of entered minus the total amount that's left, which is simply going to give you the total number of people in the zoo. When? At that time 10, because we're finding this at a very specific moment. So the explanation is n of 10 represents, or we could just say is, the total number of people, and we can abbreviate if we want to every now and then, number of people in the zoo at time t equal 10. And 10 would be 10 hours. Now you could also you could say at 5 p.m. if you wanted to be a little bit more time descriptive. And that's a great explanation. You're using your nut. Your N is noun, the U is units, the T is time. And you know what? I take that back. Time 10 is 6 o'clock, isn't it? We opened at 8 a.m., so time 10 would be 6 p.m. All right, now let's do the same thing. Find n prime. N prime of 10. Well, the thing about n prime is that if we were to take this derivative up here, and we could think about this out loud, n prime of t, we learned that one of our fundamental theorem of calculus parts allows us to simply replace this upper boundary of t in for those x's. In essence, what is happening is that the integral and the derivative that you're taking cancel each other out, and this is all that you're left with, evaluated only at the upper boundary. Second fundamental theorem. Sometimes it's called part 1 or part 2, depending on your textbook. So we can say that n prime of 10 would be e of 10 minus L of 10. All right, so we're going to go to the calculator and we're going to compute this. So the calculator all set up for us. That's what's wonderful about it. We've already got the functions defined. Let's go ahead and subtract them. And we end up with this not so pretty answer that we can hit Control Enter, and we have negative 6.227. We could even call that negative 6.228 since it's pretty darn close. But now we're going to have to interpret that. So we have to think about this a little bit. What we've got going on here is E, which is the rate at which people are entering at time 10, minus L, which is the rate at which people are leaving at time 10. So when you take those two things and subtract them, that's going to still give you this rate of change. It's the rate of change, not of the enter, not of the leave, but of the people who are in the zoo, the people who are visiting the zoo at that particular moment. So you'll say n prime of 10 is, let's say this. it represents, now I'm using the longer word, that the number of people visiting the zoo, notice I stay away from the word enter and leave. We're talking about the people who are in the zoo. We could even use the word in the zoo. Maybe that might be a little bit more clear so it doesn't confuse with enter. Plus, it's a lot shorter. So the number of people in the zoo is, would you say decreasing or increasing? I would certainly say decreasing because we have a negative value. And it's decreasing by approximately 6.228, and the units would be people per hour. When? At specifically time t equal 10 hours, which again is our 6 p.m. And that's a really good explanation. The number of people in the zoo is decreasing, right? You have this idea of the derivative is embedded into that word decrease, and the units reinforce that, okay? You could say things like the rate at which the people in the zoo is changing by negative 6.2. There's various other ways to explain this. What I like to do is lock in on one specific way that I tell my students, and I wouldn't like to detour from that very often, because if you keep saying the same phrases over and over to your kids, they typically pick up on it. All right, part D. At what time t does the model predict that the number of people in the zoo is at a maximum? So with this particular problem, what we're going to have to do now is think about what represents the number of people in the zoo. Well, I've got good news. We already know that. It is the function n of t that we saw earlier. When you integrate from 0 to t of the function e minus the function L, you end up with the total number of people. So if we want to analyze when is n going to be at a max, then all we have to do is take the derivative of n. N prime of t is, like we saw before, e of t minus L of t. So we like to find out where these critical numbers occur. When does n prime equal 0? Well, that's going to occur when e minus L is 0. And so there's a variety of ways that you can do this. You can go to your calculator, and we can solve if we have CAS features, CAS functionality. And so with this particular calculator, I have that. I can go into my algebra, choose solve, take my e of t, subtract my L of t, set it equal to 0, and solve for t. And I might want to be careful and say, listen, I only want answers that are within our domain of 0 to 12. And so I'm going to tell the calculator to just seek out those in case there are many, many, many more answers that we really would like to ignore. Now the calculator is probably going to give me some exact values, but a control enter will give me the two decimals that I seek, the 0.008 and this 8.13. Now, if you don't have that functionality on your calculator, then you're going to be forced to go to the graphing page, and you probably already have the Y1 and Y2 entries in, and that's already set up for you. I would just graph F1 of X as my e to the X. I'm going to go back in. I'm going to graph F2 as my L of X. Notice they're bold. It still understands. And now I just have to look and see, get out of the way, and see where these things intersect. But what I might want to do here as well is give you a little bit more insight into really what this graph looks like on a normal scale. Because if X is going to stand for hours, we can't be any less than 0 hours, but I might put -1 in there so I can see the y-axis. Our time interval goes from 0 to 12, so something a little bit bigger than 12 will allow me to see the right end very easily. I see a scale of 1 in my future because that's not too terribly far apart from -1 to 13. Now the y's is always the trickiest piece because we know that Y stands for the number of visitors in the zoo. We've already calculated a few things in this problem that show uh, how many visitors that we had, I believe, at 4 p.m. or at time 12 at 4 p.m. Or I'm sorry, at time 4, 12 p.m. from part A, which is about 200. So what I would say here is just to pick something, that might go from 0 up to around 200. You could go a little farther than 200, maybe 250. You just got to be kind of careful about the scale because there's not a whole heck of a lot of room here. So let's see what we've got here. And actually, I'm going to do something here. I'm going to change that to -25 so I can see that x-axis nicely. So I think now we just have a little bit better view. And there's so many other ways that you could express this. Now what I want to do is find out what is going on with this point of intersection. So I can just go into my menu, Analyze Graph, choose Intersection, sweep over, and boom, that answer looks very familiar, 8.134, which is the answer that I've gotten here. Now you can do the same thing with this intersection just down there at the bottom. It looks like it might be at the origin, but it turns out that it's just a little to the right of the origin, as you can tell. So you can also use the graphing features of the calculator to solve. Once we have those values, which I am going to write down, t is approximately 0.008 and 8.134. What we now have to do is remember that this is a contextual maximum problem, which means it's wanting an absolute. That is implied. We want an absolute maximum. So what you're going to do is you're going to go to your table, very similar to what we did with our mean problem, which was our example 4, and you're going to input the t and calculate the n of t. Now the good news here is that you only have 4 values that you have to calculate because our zoo started at time 0. We have the critical number 0.008, and then we have the critical value 8.134, and then of course we have our far right endpoint of 12. And so each one of these will be systematically plugged in for the t. Well, I'm not going to waste a lot of time with this first one, because if we integrate e minus l from 0 to 0, we know that we're going to get 0. Well, go figure. Nobody is in the zoo at time 0. The problem even stated that. Now, I don't think that we're going to get a max here, but it is part of our critical values, so we might want to go ahead and figure it out. And we can do that by just simply going back to the calculator and taking our shift plus from 0 to the 0.008, and then we just enter our e of t minus l of t. Remember, my functions are in terms of t. If I hit enter and then control enter, I've got the result. Doesn't seem very logical that this would be a max, negative 0.002. It's kind of like a false reading in a way, but it is something that is checkable, but we're going to dismiss this as possibly being our max. I got a little bit more optimism about this 8.134, so let's check him out. So we'll go to the calculator, and the beautiful thing about this is you don't have to retype everything. Just highlight that step, go back in and edit that upper boundary to not 12, but 8.134. I'm not ready for 12 just yet. That'll be my next one. And then if I hit Control Enter, 281.117 is going to be my result. Now, I don't see any reason why you would have to recreate this expression in your table. It's very clear. We know what you're doing because you have this defined very nicely on the right side. We're going to on the left side. When we do the same thing here with our 12, we're going to find out if we have a number bigger than the 281. And as it turns out, ooh, it's close, but we do not. 260.905. So what we have here are the number of people that are in this zoo at any one of these times. Now, this time here is the weird anomaly. It's like we can't have negative people in the zoo. What? 8/1000th of an hour? We haven't even opened our gates hardly. The gate is just like starting to still open. So we don't really think about that. But here is where our maximum occurs. And we could say that at what time does the model predict? Now it wants to know at what time. So we'll say the number of people in the zoo. How about this? The number of people in the zoo, excuse me, is a maximum of 281.117. I know that makes very little sense. We could round if we wanted to, but I prefer that you don't. And this will occur at time t equal 8.134 hours. That way you're kind of covered in that you have the maximum value and you have the time in there altogether. You don't have to convert this to a clock time because that would be pretty challenging. We know that after 8 a.m., 8 hours later, I believe would be 4 p.m., but we don't have to go into the loose change of how far after 4 p.m. I know these rate in, rate out problems are long. They each clocked in at about 30 minutes. That doesn't mean that it's going to take you 30 minutes to solve them. If you really know what's going on without the explanation, the teaching, you should be able to solve these in 15, maybe 20 minutes, which is putting you right on track to finish the problems on the AP Calc exam. If you get really good at this rate in and rate out stuff, you're going to guarantee yourself a really high score on one of those 6 questions. Hope this is helpful. We'll see you next time.